We're going to break down these key concepts from classical conversations this week. We're going to make it easy to teach and, dare I say, fun.
It's so exciting to see this resurgence of the classical math philosophies
Mhm.
with the quadrivium and all. And Classical Conversations is doing a great job with that using the Math Map curriculum.
I think so, too.
It really helps students see the connections between math and other areas of life, even theology and history.
Yes. There's this amazing quote from Isaac Newton in our material for this week. And he talks about God forming matter. He says, in solid, massy, hard, impenetrable, movable particles. Isn't that amazing?
Yeah, it really is.
He's describing the building blocks of creation.
And that ties in so well to the concept of closed shapes, because everything in our world, everyday experience, has a boundary. It's closed. But only God is infinite, as the source material reminds us.
It's funny because I struggle to even visualize infinite 3D space and then to try and represent that on a flat piece of paper for my kid.
It's a challenge even for mathematicians. It really is. But the good thing is the curriculum doesn't get too hung up on visualizing the infinite. Instead, it focuses on understanding the properties of shapes and how they relate to each other in each dimension. And I think that's a good approach.
So we're going on this journey through the dimensions, starting with the simplest element.
Yeah.
The point, 0 dimensions. And then we build up from there to those 3D shapes that are all around us every day.
And it's interesting because this journey mirrors the progression that's actually in the math map. It goes from those simple digits to more and more complex numbers. And then it transitions very smoothly, I think, into spatial dimensions.
You don't have to be able to perfectly picture something to understand how it works.
And you can make it relatable for kids with an analogy. Imagine a sheet of paper.
Yeah.
But it just keeps going forever in every direction.
Think about a shape, something simple like a square. If you were drawing a square but you left a tiny gap on one of the sides, would it still be considered closed?
That's such a great question. And it's a good one to get your kids thinking, because a closed shape, it has to be completely enclosed by a boundary. And that boundary, that's what lets us measure its area. It's like a fence around your yard. That defines the space.
And that actually ties back into what we were talking about before with theology. It's like only God is infinite. Everything else has a limit, a boundary.
And even those 3D shapes, like you can hold a ball in your hand, right? But it exists in this open, infinite space, 3D space.
So we've got all kinds of 3D shapes. Let's talk about the different types. Imagine you've got a pyramid and a sphere. What's the difference?
So the key difference is the surface. A pyramid or a cube or a prism, those are all examples of what we call polyhedra. They've got flat faces. But a sphere, a cone, a cylinder, those are all non-polyhedra because they've got curved surfaces.
And then we have those really cool polyhedra, the platonic solids. The tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. Those have fascinated mathematicians for centuries.
Forever.
They're so symmetrical, so perfect.
I know, they're amazing. And there's even a special formula called Euler's formula that connects the number of faces, vertices, and edges in any polyhedron. It's a neat little formula.
To make this all more concrete for our middle schoolers, think about wrapping a present, right?
Okay.
You need to know how much wrapping paper to use to cover all the sides. That's surface area. But then there's the space inside the box that the present takes up. That's volume.
Those are great examples. And they really illustrate the difference because we use formulas to calculate both of those things. But they use different measurements of the shape. Surface area is all about the outside, and volume is about the space inside.
And don't worry, the source material this week, it explains it all really well. There are diagrams and examples. It's not as intimidating as it might sound.
It's not. It's really not.
So have you ever wondered how those cardboard boxes fold up so perfectly?
Right.
It's like magic. There's a clever design behind it.
There is, yeah.
It's all about nets.
It is, yes. A net is basically a 2D pattern. And when you fold it up, it creates a 3D shape.
Like a puzzle. And that actually relates to another concept, orthographic views. Think of those house blueprints that you see. They show you the top view, the front view, and the side view of the house to give you the complete picture, the 3D structure.
It's like taking snapshots of the house from different angles and then using those to understand the whole picture.
Yeah, and those concepts, they're not just for math class.
No, they're not.
They're used in design, engineering, architecture.
All sorts of fields, being able to translate between those 2D representations and the actual 3D objects.
So now we're going to delve into some of the practical applications of all this knowledge.
Right.
Because, let's be honest, sometimes those formulas for surface area and volume, they feel a little abstract. Like, when am I ever going to use this in real life?
Right.
I get that question a lot in our homeschool.
You might be surprised. These concepts, they pop up in so many everyday situations.
Yeah. Give me some examples.
Let's start with something simple. Packing a suitcase. You're essentially trying to maximize the volume of that suitcase to fit in as much as possible.
It's true. I never thought about it like that.
And then there's gift wrapping, like
Yeah.
we talked about before. You need to know the surface area to figure out how much paper you need.
I'm seeing it. I'm
Yeah.
seeing it. But what about those more complex applications, like in engineering or architecture?
Architects use these concepts all the time. When they're designing buildings, they need to calculate the surface area of walls and roofs to figure out how much material they need, the volume of rooms for airflow, heating, and then the structural integrity of the whole building.
Yeah.
It relies heavily on understanding shapes and their properties.
So like those blueprints that we were talking about,
Yeah.
those are basically just 3D shapes, but in a 2D format.
Engineers use these same principles to design bridges, cars, airplanes, anything that needs to be strong, functional. They've got to consider the weight, the stress, how the forces are distributed. It all comes back to geometry. And we can't forget about art.
Oh, that's true.
Sculptors use their knowledge of 3D shapes to create their masterpieces. Painters, they need to understand perspective,
No.
which is all about manipulating 3D objects on a flat canvas.
So even something as abstract as art, it still relies on these basic principles.
It does. It all goes back to that idea that math is a language that describes the world around us. And the more we understand that language, the more we can appreciate the beauty.
It's true. So can we talk about those platonic solids for a minute? There's just something so mesmerizing about them.
I agree. They really are like the rock stars of the polyhedra world.
Hmm.
And for good reason. They've fascinated mathematicians, philosophers, artists for centuries
Yeah.
because of that perfect symmetry and mathematical elegance.
So can you remind us what makes them so special?
So first of all, there were only five platonic solids, and each one is made up of identical regular polygons. Regular meaning all the sides and angles are equal. So like a cube, it's made up of 6 identical squares.
Right.
And they're the only polyhedra that can fit perfectly inside a sphere, with all their vertices touching the sphere's surface.
It's like they're meant to be.
I know.
Are there any real-world examples of platonic solids? Or are they just like a theoretical concept?
No, they actually do show up in nature. So for instance, some crystals and molecules, their structures are based on platonic solids. And believe it or not, some viruses, they have a shape based on an icosahedron.
That's crazy. So nature really does follow mathematical patterns.
It's pretty amazing. And those platonic solids have even inspired artists and architects. You can see their influence in everything from ancient Greek sculptures to modern architectural designs. The material actually includes instructions on how to construct your own platonic solids using nets. And while we're on the topic of nets, remember those orthographic views that we talked about earlier?
Oh,
That whole idea of representing a 3D object in 2D?
like those blueprints, yeah.
Yeah. So those orthographic views, they're basically a way to show the object from different perspectives, the front, the top, the side. Imagine you're taking flat pictures of a 3D object from different sides.
Like a series of snapshots.
Exactly. And those views are so important in engineering and design because they allow you to communicate the exact dimensions and details of an object accurately.
So it's not just about drawing a pretty picture, it's about conveying very specific information.
Precisely. It's a skill and it takes practice. But once you get the hang of it, you can start to see how those 3D objects translate into those 2D representations.
And vice versa. Being able to look at a set of orthographic views and picture the 3D object, that's pretty cool too.
It is. It's like solving a 3D puzzle.
Speaking of puzzles, those surface area and volume calculations can be a little tricky, especially at first.
But they don't have to be scary. The key is to break them down, step by step, and really understand what each part of the formula represents. Visualizing the shapes.
Yeah.
And labeling the different parts, that can really help.
I find that my kids, when I encourage them to draw diagrams of the shapes, they seem to understand it a lot better.
Oh, absolutely. And
Yeah.
you know what? Don't be afraid to use online resources and videos for extra support. There's so many great tools out there.
One thing that I struggle with, and I know some other homeschool parents do too, it's remembering all the different formulas for every shape.
The good news is there are patterns and connections between the formulas, so you don't have to memorize each one like in isolation.
Tell me more about that.
For instance, the formulas for prisms and cylinders, They're very similar. They both involve finding the area of the base and then multiplying by the height.
So if you know one, you can figure out the other.
Exactly. And the same goes for pyramids and cones. They both involve finding 1/3 of the area of the base times the height. It's more about understanding the underlying principles than just memorizing a bunch of isolated formulas. And you know what? The more you practice it, the more confident you'll become.
That's true with anything, but especially math. I'm feeling so much more equipped
Yeah.
to tackle this week's material with my homeschoolers.
That's what we want to hear.
I'm not as intimidated by it anymore.
Good, good. We've explored the foundations, the practical applications, even some of those philosophical and artistic connections. Who knew math could be so multifaceted?
I know, right? And most importantly, we've given you the tools and strategies you need so you can confidently guide your homeschoolers through this. You've got this.
You do. Embrace the challenge. Have fun on your homeschooling journey. You are not alone.
Absolutely. Until next time, happy exploring.
Who's this?